In the last couple of videos, I've looked at some computer-intensive methods that can be used in the context of hypothesis testing. So we looked at permutation tests and simulation. But in this video, I'm going to focus on a different type of computer-intensive method called bootstrapping that is used in the context of estimating standard errors and confidence intervals. So the first example I'll look at is this study of the language center in chimps' brains, and here's a histogram of Brodmann's area 44 asymmetry score for 20 chimps, and we can see that it's not a symmetric distribution, it's skewed, and so we're going to use the median, the sample median, to estimate the population median. And we don't have a lot of theory to help us if we are trying to figure out the sampling distribution of the median. There's lots of theory around for the sampling distribution of the mean, but not as much theory about the sampling distribution of the median. And so we need a different method for assessing standard errors and confidence intervals, and so the method we'll use is the bootstrap. So here is the sample median, it's 0.14, and so we want to get some sense of the uncertainty around that estimate. And the way that we'll do that is using bootstrap samples. So here's an example of a bootstrap sample. Let's put it side by side with the original data. So there's the original data, and there's the bootstrap sample. So the way the bootstrap sample works is it takes the sample and picks one of these numbers at random. So 1.19 is the first number it picked. And then 1.19 is put back into the sample again, and a second number is picked at random. So minus 0.22 is the second number. And then so on. And so this is sampling with replacement. So if we remember back to when we looked at permutation tests, a permutation is sampling without replacement. When we looked at simulation, simulation is based on sampling with replacement, and now we're looking at bootstrapping, and a bootstrap sample is sampling with replacement. We can see that it's possible for each value in the original sample to be picked more than once in the bootstrap sample. So let's see if I can find one there. So I've got minus 0.24, and then I've got minus 0.24 again. Okay, so what do we do with the bootstrap sample? Well, we could calculate the mean for the bootstrap sample. So 0.01. And we could do that a bunch of times. So if we do it a whole bunch of times, we'll get an estimate of the sampling distribution of the median. So that's what the bootstrap does. So we're going to run 10,000 bootstrap replicates. We'll set up a results vector to store our results, and then we'll run the loop 10,000 times, and then we'll look at a histogram of the results. So this histogram represents an estimate of the sampling distribution of the median in this case. And so we can use this estimated sampling distribution to calculate a standard error and to calculate a confidence interval. So we'll come to those two quantities in a second. Let me just briefly mention what happens if you calculate the mean of the sampling distribution. We would expect this number to be pretty close to the actual sample median, and it is. In more complicated examples, these two values can differ by more than they do here, and in such a case we might want to make an adjustment for that bias. And so that's going a little beyond the scope of this course, and so we're not going to talk anymore about bias, but it is possible to adjust for the bias in more complicated examples, but we're not going to worry about that here. Instead, let's look at the standard deviation of this sampling distribution. So remember, the standard deviation of a sampling distribution is given the name standard error. And so this is the estimated standard error for the median in this example, so 0.085. So that's one way to measure our uncertainty in our estimated median, is to report the standard error. Another method is to come up with a confidence interval. So the way that we're going to calculate the confidence interval, there's different ways of doing this, but perhaps the simplest way is, because this represents the sampling distribution, if I figured out the 2.5th percentile of this distribution and then the 97.5th percentile, I would have 95% of the distribution in between, and so that is giving me an estimated 95% confidence interval. So that's what this quantile function does here. So we can say we're 95% confident that the population median is between minus 0.075 and 0.310. Turns out that someone wrote a function, actually a whole package full of functions that does bootstrapping. So rather than doing all this coding ourselves, which can be challenging, we can instead use the boot function, which is in the boot package. So all we have to do there is write a function that will calculate our estimate. So in this case, our estimate is the sample median, and then use the boot function on the data. Here's the data, and then here's our function that we just wrote, and this is the number of replicates. So if I run that code, then we get our bootstrap results. Here's the sample median. Here's the bias that I mentioned briefly just now that I said we're not going to worry about, so we're going to ignore that. And then here's the standard error. So pretty close to the one that we calculated. What did we get? We got there 0.0847, and here we're getting 0.0881. So it's not going to be exactly the same, because every time we run the bootstrap we're doing random sampling, and so our results are going to be a little bit different each time. And let's use the boot.ci function to calculate a confidence interval. So the confidence interval to 3 decimal places is the same as the one that we got. That was what we got before. Minus 0.75, minus 0.075, sorry, up to 0.310. Okay, let's look at another example. Let's revisit the data set on crickets, female crickets that were sagebrush crickets that were either starved or fed, and the time to mating was the response variable. The first time we looked at this data set, we decided we couldn't use a two-sample t-test because the distributions of the starved crickets and of the fed crickets, neither of them looked especially normal. And so that was an assumption that was required for us to use the two-sample t-test, and that's why we ended up using the Manwood EU test, and that's why the permutation test was useful as well in that example, because that doesn't rely on a normality assumption either. With non-normal data, it turns out that the median is often a more useful measure of the center of the data than the mean is. And so that's what I'm going to look at here. I'm going to look at the difference between the sample medians of the two groups. So it comes to minus 9.8. I don't have a lot of theory to help me with the sampling distribution of the difference between two medians. And so I'm going to use the Bootstrap to come up with an estimated sampling distribution, and that will allow me to assess the uncertainty in this estimate. So to use the Bootstrap, I'm not gonna worry about writing a loop like this. Instead, I'm going to use the boot function. To use the boot function, I need to have a function that's going to calculate the estimate that I'm interested in. So that's what I'll do here. Here's a function that will calculate the difference between two medians. And then I'll run the Bootstrap on the data with my function that I just created, and I'll create 10,000 Bootstrap replicates. So I'll run that, and here's the results. So here's my observed difference in the medians, minus 9.8. That's what we got before. We're not going to worry about the bias. And there's the standard error. Let's take a look at the sampling distribution in a histogram. So there's the sampling distribution, or an estimate of it. And finally, let's calculate a confidence interval. So we're 95% confident that the difference in the medians is between minus 60.8 and 12.2. So in particular, 0 is inside this interval, and so if we're interested in the difference in the two groups, we can't rule out that the difference in the medians could be 0, because it's well inside this interval. So that kind of reinforces the conclusion we ended up with when we used the permutation test on this data and looked at the difference in the means. We weren't able to reject the null hypothesis that the means were the same, and here this confidence interval also seems to indicate that a difference in the medians of 0 is pretty plausible as well. So that's a couple of examples of using the Bootstrap to estimate standard errors and confidence intervals. So the last 3 videos we've been looking at computer-intensive methods, so permutation tests, simulation, and bootstrapping. The next video in this sequence isn't really a computer-intensive method per se. It's kind of a different topic, but it's what we're going to consider next. So we're going to look at survival analysis.